Hi, good afternoon, everyone. I'm Nick Perrin, back on the SimScale F1 workshop for the second time. Very excited about it. I'm glad we've got many people again today. So today we are going to talk about the slipstream effect on Formula One cars. We are going to do again a live post-processing in Paraview. So you can follow every step of opening and opening the files and looking into the flow around the cars. So we're going to do this together. I'll show you some videos, or rather some slices going through the cars again, so we can see exactly what is happening with the flow around the car. And we'll have a question and answer session, which for me is really interesting and is the way to interact with you. So I'm inviting you to post your questions. You can start now, and obviously Milad will help us to select the questions that I'll answer, and we'll take it from there. Okay, so let's start with a quick introduction. If I switch to some slides now. Okay. So today we want to look into what's happening when a car is following another one from very closely, and what we call the slipstream in Formula One. You can see that a lot happening in straight lines, obviously, when somebody is trying to gain an advantage, a speed advantage, to eventually overtake the car in front under braking. Why do we follow closely a car? The effect of following the car is to reduce the drag and downforce on your own car. It's pretty simple to understand, but it's pretty significant. The drag and downforce can be reduced by up to 50% if you follow the car very closely. And you can see on this picture the mechanism. Obviously, the wake of the first car is significant and is affecting the speed and the velocity of the air that's going to hit the second car. And we look into some details of this in Paraview, and you will see exactly what sort of magnitude of speed we get behind the second car. And then you can see the effect on the pressure, the static pressure on the wings and on the diffuser, in the floor, explaining why we lose so much drag and downforce. Obviously, if you lose 50% of your drag, keeping in mind you have to be really close to the first car to do that, you can imagine the speed advantage you get. We are talking 20, 30, or 40 kph if you would carry on following that car. Obviously, you have to offset yourself at some point, and the drag is increasing again. So it's pretty obvious on this picture how the drivers are using it. You can see on the bottom picture, this is a button following another car from very close. Sometimes it's pretty close actually, and they tend to have to be careful to not hit the car in front when they offset themselves. It's quite good for the show, I guess, and the spectacle of Formula One. But if we look a bit closer at what's happening, and I've just put a couple of images here. The first one is the velocity in front of the first car. So you can see the section of the nose here. So it's right in front of the first car. That's taken from the simulation that we'll open together. And obviously the velocity is close to infinite velocity, so basically 60 meters per second in our case for this simulation. And in front of the second car, the picture is completely different. There's a big drop in air velocity, specifically in the lower part at the front. That's coming from the diffuser of the first car, and that will have a big effect on how much downforce and drag is produced from the floor area and the front wing of the second car. but the effect is going much higher than just the nose and the front wing. It's going to even interact with the rear wing of the second car. As you can see, the wake of the first car is probably up to 2 meters high at this point, so well over the height of the second car. So it's going to have a big effect. Velocity is not the only effect of the first car on the second car. You can see the actual flow angle, and again, we were talking last week a lot about vorticity. You can see here rotational flow. So you can imagine that the actual flow angle hitting the front wing is not straight on the second car. And you will also have some sort of energy loss, pressure loss in the flow. So your total pressure is going to drop as well. And you know, if you don't have energy or velocity or total pressure hitting an aerodynamic component, then it's not going to work. As we said again last week during the basic principles of aerodynamics, to get a static pressure and a force on your wing, it has to come first from energy, total energy of the flow around that wing. And that's why I want to talk about the effect of this principle on car design. We are talking about slipstreaming, so two cars following each other, but you can actually think of only one car, and the concept of wake and loss of energy is very much applicable on just one car. And really, the back end of the car, the diffuser and the rear wing and the floor are actually in the wake of the front wheels and the front wing. So slipstream of the front wing and front wheels will have a big effect on the performance of the rear at the rear of the car, exactly like the performance of the second car following the first car. And just as a little game, you could think of removing a front wing on your Formula One car, and you would notice straight away a big increase in rear downforce, purely because you make the flow energy much better, much bigger going towards the rear of the car. And I'm saying this is typically something that we do as well in Formula One teams sometimes. I've done it in the past. You will remove your front wing in the wind tunnel and measure your rear downforce gain. You will always gain rear downforce, but how much are you going to gain is very interesting to compare with your CFD results. This is a very good way to do some correlation work and check that the effect of the front wing on the rest of the car that is simulating it in CFD is effectively correct and well simulated, and that in the wind tunnel you recover the same offset, as we say, so an offset of rear downforce and drag as well. This test has also been done on the track, and obviously you can't drive around in this configuration very fast, but in the straight line you can measure forces. So it's sort of an interesting test to do. The third test would be to remove the front wheels, and obviously it's not something that you can do on the track, but you would notice another big gain of rear downforce if you would do that. And this is just to illustrate the wake effect of a component in front of another component. So as a designer, to optimize a Formula One car, you really have to not only work on the shape of the component you want to improve, but also think of what's in front of it. So the front wing that's why the front wing has got such a huge importance in Formula One, not only to improve its own performance, but to make the flow behind it more efficient, to make sure it clears the floor, for example, the sort of low energy area coming from the front tires, make sure the front wing is sort of pushing this low energy flow outboard so it won't go under your diffuser and floor area. So this is very important for car design. And again, another illustration of wake effect and loss of energy downstream. If you look at just a single car, so this is a slice through the car at the rear wheelbase level, so cutting through the rear wheels. And this is the end of the engine bay. You can see the floor, and that's where your diffuser is going to start. And the color is velocity of the flow. Well, basically, the red zone under the floor here in the middle is indicating of a high energy flow. This is really good to have this in the center of the car like that, so you know that your rear diffuser is going to have a good energy flow to work with. But on the outboard, you can see some patches of yellow and orange here. So some of the wake of the front wing and the front tires have actually come back inboard. And that's going to lose some performance in your diffuser. You can see that each side. But look at what's happening on top of the floor. All this area, so between the rear tires, there's no red at all. This is all sort of green, yellow. So velocity is going to drop in this area to maybe 20 or 30 meters per second. And this is also part of the wake from the front tire. We have pushed it up so it actually goes over the floor rather than under the floor. So you won't lose as much in your diffuser, but this is going to explain why we lose some performance in this area. So you also want to make a bit a cleaner flow going towards the rear of the car in this area. The fact that this a bit higher of this zone, you can see again some red patches, so a bit more energy there, and that's going to help the rear wing to perform better. And the last slide is the same slice, but a little bit further. And we are now looking at slightly behind the rear tires. This is the end of the rear tires. And we're still into the diffuser area, right in the middle of it. And look at the wake of the rear tire. Look at this blue patch. So very low energy. We've lost a lot of velocity. And this has been sucked inside the diffuser. And it's really going to lose some potential performance in your diffuser. So a lot of the work around the rear tire is to try and push this blue patch and keep it sort of outside of our diffuser. We don't want this blue zone to intrude too much into the diffuser. I was saying that the rear wing is protected from this problem. You can see that the energy of the flow is generally pretty good going to the rear wing. Obviously being a bit higher is easier. Okay, so if I come back to just running the simulation, you remember, you can come on the website simscale.com/F1. And we are now looking at the second simulation. So you've got a button here, you can open the simulation, slipstream. And I won't show you the further steps, but obviously you can log in if you've got an account or create one. You can switch to the simulation tab, and then you can click on Start button so you can perform the simulation yourself. And there's instructions. If you're a bit lost, you can use these resources here with some links, so that can be helpful for you. Okay, so let's move on to look into Paraview now. Same as last time, this is the post-processing that we want to achieve, but I'm going to close Paraview and we're going to redo the steps together. So it's easy for you to achieve the same later if you want. So I'm going to close Paraview, open again, okay. And we're going to go and open our simulation. So we're into sim number 2, and I'm going to open case.foam. Don't forget to switch to time number 1, which is the last time available. Otherwise, you're not going to see anything in time 0. We are going to select all the mesh regions to start with and apply. And that's going to load all the parameters and the model, the complete model. So this is going to take a few seconds. Don't forget you can download Paraview for free from paraview.org, so everybody can perform this analysis later. Okay, so we're still waiting for the upload. It's nearly finished. Click on the eye if you don't see anything. And again. Okay, that's good. So remember, we've loaded everything. So what you see is the complete box. You can see 2 cars here. So the same as last week, we want to extract each car individually so we can look at them more easily. So we're going to go back to filter, recent, because we've been using them, extract block, and we want to select the first car to start with. So you need to go F1 step, wheel front, and wheel rear, and hit apply. Here we go. This is the first car, and we want to do the same for the second car. Go back to case.foam, filter, recent, extract block. If you don't find it under recent, you go alphabetical, you've got all of them there, and you go extract block. And this time we're going to take F1 step underscore T, wheel front underscore T, wheel rear underscore T, and apply. The last thing I want to do is to make sure that we visualize into parallel mode, so without any perspective. It's just a little bit easier to zoom in and out. I think you have to hit advanced properties, and you click on camera parallel projection. Here you go. We're going to do a fit to screen, and now we've got both our cars here. We are looking at pressure, static pressure. You've got a scale on the right-hand side. But same as last week, we want to change the scale and make it a little bit more readable for F1 aerodynamics. So we're going to go here, and we select a range going from 1,800 to minus 3,600. And as I said last time, this is roughly looking at a static pressure coefficient between -2 and +1. Okay, hit rescale. Right, so we've got a lot of green, some red, some blue. So if we look at under the cars and zoom, the first car has got, you can see some suction under the front wing in the diffuser area, but the second car doesn't have as much suction. It's lost pretty much all of it in the diffuser and under the front wing. If I look on top this time, top of the cars. The first car's got static pressure building up on top of the front wing and the rear wing, but you can see the second car has lost quite a lot of static pressure. So it's very easy to see what's happening here. It's basically like a detuned car. The second car has got less energy to work from, and therefore all the static pressure is minimized. Okay. Again, we want to look at the wake in a slice. So let's create a slice. Don't forget to select case.foam here. And then we're going to go filter and slice. We've done this before. We don't want to see the plane. Origin is going to be 0, 0, 0. Okay. And it's going to be along the y-axis. Okay. Apply. Perfect. So we've got our slice in the center. This is colored by pressure. Here we want to color it by velocity, so U. And again, the scale is not quite right, so we are going to change the scale, and we're going to go to 60 here. So we want to look at the velocity between 0 and 60, which is the speed of the simulation, 60 meters per second. Here we go. Go along the y-axis, zoom, and now we've got a nice picture of the wake. You can really see the height of the front car's wake and the second car being into it. So it's pretty obvious. If I zoom a little bit in front of the second car, you can really see the loss of energy going under the front wing at the center of the second car. So there's going to be a lot of losses going on there. Okay. I'm going to zoom again like that. And the last thing I want to look at is producing some streamlines. So we can see where the flow is coming from when it's hitting the second car. So we want to select case.foam again to have the field, and we're going to create some streamlines. Here we go. Okay, so you can either have a point source or a line source. It's a little bit easier to look at a line source streamline. And the first one we're going to create is the one in front of the first car. So same as last time. So it's going to be -1 in X. Y will be between 0 and -1. And Z I will put 0.07 meters up. Okay, now I hit apply. And I want to color the streamlines by velocity. And I need to change the scale again. Here we go. So we've seen last time the flow is obviously completely straight, 60 meters per second, very clean. And that's going under the front wing, nice and clean, full of energy. Perfect. So we're going to move this streamline in front of the second car to compare. So we're going to just change the coordinates, the X coordinate to be 5 meters. So it's going effectively in front of the second car. And you can see that first of all, the velocity of the lines is reduced a lot. So how much have we got? So we've got some blue and green. So we are looking at 15 to 20 meters per second. So a lot of energy lost there. And the other thing is the angle of the flow. Some of the flow is actually coming off the top of the rear tires of the first car. So that's going to have a relative angle to the X direction. And at the center of the car, the flow is got a very vertical angle now, so a lot of movement going on. So obviously the car that you've been optimizing for straight flow is not going to work at all the same way when the flow is disturbed this way from the first car. So this is it for the Paraview analysis. And obviously, if you have any questions, we can come back to it a bit later. And the last thing I'm gonna show you is the images that we've been creating before the workshop, slicing through the car. So opening that now, colored by velocity, and you can also see the direction of the flow. So this is in front of the first car. Again, we can see the high energy flow hitting the first car, and you can see the direction of the flow is pretty straight. Obviously, the vertical lines indicate a very small vertical component of the velocity, but in fact, the flow is effectively very much in X direction. And I can move forward. So slice through the first car. I'm now looking at the very end of the first car. This is what comes off the first car. Again, a lot of rotational flow coming off the diffuser. This one is coming off the rear wing. This is coming off the side of the rear tire. And this is what's gonna hit the second car. As we can see now, this is the second car. And this is a good way to look at effectively where the different vortices of the first car go and hit the second car. But in a nutshell, and to conclude on this, when we design the Formula One car, we are not really optimizing the car for slipstreaming. We are not really optimizing in the wind tunnel or in CFD by simulating following a first car and try and optimize your car for it, because it would go against optimizing the car when it runs on its own. But it's still a very interesting thing to simulate from time to time and see how much drag is effectively shed when you follow the first car. And again, I think the interesting point is, generally speaking, we really need to keep in mind when we design the front wing or the front tire devices, how much rear downforce can be gained if you have a really good management of the flow from your front wing or the front end of the car. So I think now would be good to welcome some of your questions. Hopefully we've covered some interesting subjects for you. So Milad, if you want, we could start answering some questions.
Yes, hi, I'm back. Thank you very much, Nick. And Nick, the first question for you is from Juanit, and he wants to know how this, or if the slipstream affects the white 250 vortex.
Yes, it will, definitely. The Y250 vortex, we talked about it last week, so I can show it again. I'm coming back on some slides we were looking at last week. But basically you can see on the front wing of the car, there's a big discontinuity between the center section and the outboard. And there is a big vortex that will be shed off this edge, of the edge of the wings here. And that's a big driver of how the flow is managed going to the back of the car. So effectively, if you follow a car, this Y250 vortex is not going to be produced the same way. It is only produced because you have a big suction going under the front wing on the outboard side and not so much on the inboard side. But when you follow a car in the slipstream effect, effectively that the suction created by the front wing is going to be much smaller. So you can imagine that your vortex is going to be much smaller as well. And if it gets too small, it won't even exist. So effectively, the Y250 will be perturbed a lot.
Thank you very much, Nick. Next question by Akrem. He wants to know how the contact patch height of the rear tire influence the diffuser performance, and what's the standard contact patch height used in CFD simulations.
Hi, Akrem. So the question regarding the contact patch height, I guess, is asking the size of the contact patch. So if I come back into Paraview, and I hope I can show what we are talking about here. So I'm going to look under the car. I'm going to hide the streamlines, which will make it a little bit easier. Here we go. Okay, so we are looking at under the second car. You can see this shape here, the sort of egg shape. This is the contact patch of the tire with the ground. The tire is not touching just on one point. Obviously, it's sort of creating a patch area. The size of it can vary, because you can imagine that if your tire pressure is a bit bigger, is a bit higher, your contact patch is going to be a little bit smaller. If you drop the tire pressure, your contact patch is going to get a bit bigger. To know the exact shape of the contact patch is not always easy, but in CFD we have to agree on which contact patch size we want to use. So from my experience, I know that this sort of contact patch is an average size, and is working well on average. The sort of wake of the rear tire that will go inside the diffuser this way. So you see where this very blue zone here, this is creating some jets, which is this very low velocity flow, and that is sucked in the diffuser. We've seen that on the picture before. Okay. The size of this jet depends on the shape of the contact patch. So you can imagine that if you vary the contact patch area, the flow going into the diffuser, sucked in the diffuser, will change. And it can be very sensitive. It can have a big effect. Sometimes you go from one state to another state. We've tried in the past, even on the racetrack, to increase the tire pressure so that the contact patch will get a little bit smaller, and see how much downforce was gained. And so this is something to keep in mind. Effectively, the tire contact patch is something we have to remember to study different sizes and see the effects in the diffuser.
Yeah, thank you, Nick. Junaid has the next question, or two questions. First of all, he wants to know if there is any way of minimizing losses due to slipstream. And the second question is if you guys are optimizing your rear wing to make it more difficult for the car behind.
Yeah, it could be a good game to do that. The honest answer is no. We don't optimize the rear wing to make sure the guys behind to make their life more difficult. No, we don't do that. It's already a lot of work to optimize your car so that it is fast on its own. So we optimize the rear wing to make sure it's it's performing very well on its own. We are not really looking at the slipstream effect and how much we're going to hurt the car behind. No, we are not doing this. As for do we optimize the car to make sure it doesn't lose too much downforce or drag in the slipstream? No, we are not doing this neither, because again, it would be far too much work. We tend to optimize the car on its own.
Well, Alberto would like to know if increasing the width of the neutral section of the front wing could make overtaking easier.
Well, this is a big debate of how can we make overtaking easier. So I come back on this picture. You know, people are trying to understand how cars could follow each other without losing too much downforce. Because if you do that, you can imagine that it would be easier to overtake, because you could stay closer in corners and benefit from slipstream early on in the straight line, and then you'll be able to overtake more easily. There's been a lot of studies done in wind tunnels and by the FIA as well. Back in 2007, I remember. And part of this study effectively was to come up with this central section here. So the wake of the first car is this, as we've seen in Paraview, the wake of the first car is very significant in the middle, what's going under the nose. So part of the reason why we have this section here is so that the car can still keep some front downforce even when it follows the first car. So yes, this is helping. And the question being, if we make this central section wider, is it even easier to follow the first car? Maybe. To be honest, this is something that would have to be tested in a wind tunnel. I am not too sure. You know, the effect of following the car, first of all, is that we are losing a lot of energy pretty much everywhere. So I'm not sure how significant it would be to work on details on the car design to make sure it can follow the other car. I think it is from the DNA of Formula One and from the sport, it will always be difficult to follow a car. You will always lose some downforce. There's not much you can do about it.
A lot of people ask about the CDG wing, this splitted rear wing, which was proposed some years ago. Do you know exactly? Did you also look at the solution when you was at Williams, or what is your opinion about that?
Okay, hopefully we can find a picture here. Yes, we can. The CDG wing, you can see a good example here. You can see the rear wing is split. Instead of being in the center, you know, it's in two parts behind the rear tires. The idea is that if you follow a car, the rear wing is going to be less disturbed this way because towards the rear, effectively the way it works, it's not so big behind the rear tires. I remember when the FIA came up with this picture, and that was again back in actually 2006 on this picture. And we started to think that we were going to use it, so we looked into it. The problem with it, first of all, is it's very difficult structurally to make it work. You can imagine that to have a wing that's stiff enough on the outside like this, you can only attach it on one side, not on the other side. It's pretty difficult, and that's why it's been discarded, I think, at the end. The other thing, I think, aesthetically, it's not great. You still want, you know, the car to look nice. But was it easier to follow a car with this rear wing? It's never been tested on the racetrack, so I'm not too sure. I think from CFD, yes, there was some sign, but again, I don't think it was significant. So I think it was a good idea to not use it at the end.
Okay, thank you, Nick. Matthew would like to know if you can show us how to calculate downforce and drag numbers in Paraview. I don't know how much time it takes. If it's maybe not fitting into the scale right now, we could also prepare something on the FAQ page.
Okay, yeah, this is, it's not something that we're going to be able to do quickly here, but it's possible, obviously. Normally it's done automatically during the simulation anyway, so you can get forces. You don't have to post-process yourself. But Paraview is giving you the pressure, the static pressure on the body. So what you will have to do is to extract, first of all, the normals of each cell on the body. So to know which direction the orientation of the cell is, its area as well. And then you know the pressure. So you have to multiply the pressure by the orientation and by the area. And then by summing all this on the body of the car, you get the force. So you can see it's not straightforward, but you can do it, and some of it will involve using what we call a calculator. So if I show this one calculator, that will allow you to perform this sort of calculation in Paraview. So it's possible. I'm not going to do it here. Maybe we'll get it ready for the next session for you.
Yes, there's also a blog article in our SimScale blog where it's, I think, nearly everything described, and we will put it also on the FAQ page today or at Monday, so then you can look it up there in the worst case. Kushal has a question. What will be the effort of the downforce when the front wing height with respect to ground level is changed, and also how the height affects the ride quality?
So the question is how the height of the front wing affects the ride quality?
Yes.
Okay. So I think the first part of the question is how much downforce change will you get when the ride height of the car is changing? I don't have the numbers to show you here, but effectively it's very sensitive. I want to show you something first. If I look at the simulation that we have at the moment, you can see the ride height that's been used. You can actually see that the car is parallel to the ground. So the ride height is actually pretty high at the front and actually quite normal for the rear. So normally the front will be lower. So we do that in the future and for the simulations, and the rear will be about the same. So if you drop the front wing is going to get much closer to the ground, and that will gain a lot of front downforce, yes. It's some sort of exponential relationship as well. You know, if you halve the distance between the front wing and the ground, you get probably 4 times the forces at some point. So it sort of increases. It's higher increase than a linear increase. So if you get really close to the ground, you can imagine the forces are getting really high. But that said, we design the front wing always at the minimum height. If I come back to my design view here, and if I show you the box in which we can design the car, if you remember last week, you can see that the front wing has to sit in this box, and it's been designed, you know, as low as we can. It's nearly touching the bottom of the box here, so within 1 millimeter. So you cannot have it lower than this. The only thing you can do on the track is to run the car as low as you can at the front until it's going to touch at the very front of the floor here, and that's where you can. That's when you can see all the sparks going off the cars, because the car is touching at the front here. So yes, we are trying to lower the front wing as much as we can, but we can only do it by running the car as low as we can. And this is why we are running stiff suspensions as well.
Okay, thank you. Next question is by Bruno Schechter, and he wants to know if there is any notable effect on the front car when there is another car slipstreaming.
So what notable effects? Obviously, there is a loss of downforce. We talked about it a lot.
I think he's talking about the car on the front.
Oh, the car on the front. Sorry. Okay. Yeah. No, there's no effect. I think if the car behind is very, very close, you could start to sort of block the exit of the diffuser a little bit, so your diffuser wouldn't work as good. So you would lose a little bit of rear downforce. Yes, but the front car would have to be really close, and I don't think this really happens in reality. Also, it's only the tip of the nose, so it's not enough to block the diffuser. So yes, there could be a very, very small effect, but I don't think we can measure it.
Maximilian Hirsch wants to know if the tire rotation is considered in the simulation.
Yes, it is, absolutely. It is. I think I can show it here. So, if we wouldn't have tire rotation, the forces would be very different, and the flow around the tire would be very different. So it's very important to have the wheels turning, as well as the floor effectively moving like it's relative to the car, exactly the same as in reality. If you take the first car, so extract block number 1, and if you color it by velocity, it's very clear here. You can see in red the actual surface of the tire, the outside surface, is rotating with a velocity of 60 meters per second because it doesn't have a relative velocity with the ground at the contact patch. So yes, it does.
There's a question by Joel, who wants to know what is the CD and CL value of a F1 car, or in which area these values are.
Okay, so some basic numbers about downforce and drag on the F1 car. What I can say is that the efficiency of the car, so the L over D, which is an interesting number to look at for an F1 car, will be anything between 3.5 and 4. It will depend on the ride height you're looking at. It will depend on also, are you in the configuration to go to Monza or to Monaco? It depends on many parameters. But this is a ballpark number for sort of good developed car. Interestingly, the car that you see on screen, as I said before, it hasn't been developed yet as much. We want to spend much more time on it to increase that number. So the L over D of this car is lower than this at the moment, but we know where we should be, obviously. As for the drag and downforce themselves as a number, so I gave you the ratio between downforce and drag, but in terms of drag itself, if you talk about SCX, so that incorporates for the frontal surface of the car, it would be below 1, so you're looking at numbers between 0.9 and 1. Again, it depends on the configuration, so then you can derive the downforce number. So these are the sort of typical numbers for an F1 car.
Another question from Bruno. He saw that two cars together could act similar to a very long car, perhaps reducing the drag on the front car as well. Is there any comparison you can do, Nick, or is it not like two cars acting similar like a long car?
Well, again, I said if the second car would be really close, you could imagine that the diffuser and maybe a little bit the rear wing would be affected. So they would create a little bit less downforce, so therefore a little bit less drag. And therefore the front car, yes, would have a little bit less drag. But I don't think this is significant. To be honest, it doesn't really happen in Formula One. You are not close enough for long enough for it to be true. If you look at drag racing on oval in America, for example, especially with the bigger cars like the NASCAR, that's got a much bigger frontal surface area. You could imagine, it's probably true that in this case, the second car will have an effect on the first car. a little bit, but not in Formula One, no.
Okay, Nick, there are some more questions. Several people asked in the meantime if the hot air leaving the car has any effect on the car behind.
Yes, this is a good question. Effectively, we haven't talked about it. Another effect of slipstreaming is the thermal effect. So the air from the first car is going to be hotter than ambient, which means its density is going to drop. And density is coming into play when we talk about total pressure. And remember, total pressure is energy. This is what drives wing static pressure and performance. So yes, the hot air is going to drop the density, that's going to drop the total pressure, and it will have another sort of effect into losing downforce and drag for the second car. Obviously, there's another effect, which is if you drive into hot air, then you're going to have problems to cool your brakes and your engine as well. This is something that could be simulated in CFD as well. We could add hotter air going off the first car and see what the effect is.
I think we have time for some more questions. So if you have some questions, just put them into the chat, into the question box. Emanuela wants to know if unsteady results and steady results have a big difference in F1.
So I think we had that question last week, so I will relate to it. I think we're talking about doing a steady state simulation or an unsteady simulation in CFD. So again, the simulation you have on screen here, this is called a rounds simulation. This is like a steady state CFD simulation. So the equations behind are slightly more simple than a non-steady state, which means we can solve them quicker, and that's what is used most of the time. If you go to the non-steady and what we call DES, detached steady simulation, so that has some time-related flow structure. This is a bit more complicated to compute. It takes more time. Does it have a big effect on the results at the end? Yes, it can have a significant effect in some cases. I've seen in the past sometimes the forces changing by 5–10%, depends on the car you're looking at. Most of the time it will actually perform a little bit less. And you can see the wake is moving behind the tires like it does on a real car. The flow behind the tires in the wake is actually unsteady. But again, the computing time is so much bigger that it is really hard to develop the car using these equations. I'm sure in the future, when the computer gets much bigger, we can use unsteady simulation more often.
Tim wants to know if you can detail the tuning of the diffuser and maybe show how you are going to improve the diffuser or to develop the diffuser.
Okay. I'll try and show quickly from this view. So the diffuser here, there's two main parameters, I guess. The profile of the diffuser itself. So if I slice the car, so we can see it better. Okay. So now we can see clearly the profile of the diffuser itself. So by regulation, the diffuser will have to start here. This is what we call the kick. And it will have to end here at this maximum height. You can do pretty much what you want between these points, but it cannot go higher than this height anyway. You can see that the profile I have at the moment is got two, well, actually three sort of different areas. So you've got, we call it a ramp. So you've got a first ramp here, and then a flatter section, and then a kick at the end here. This is coming again from experience, having developed diffusers to find that this shape is working better than maybe a more simple shape. You can do a pure straight line, so a long ramp, but the performance of this section here works a bit better. So part of the work to develop the car will be to move this profile around, so make maybe the ramp a bit steeper here, a longer flat section, and try. And I really like this sort of process, because you've got your model and you just move it a little bit around, morph it, and see if it's better. So that's the first thing you would look at. Once you find a solution that works and that's difficult to optimize, first of all, you can decide if you want this profile all the way. So you can make it the same profile along the width, or you can vary the profile in 3 dimensions. Actually, we've got in the center of the diffuser, you've got what we call the boat area. Because of the change, because of the step in the plane before, we have this shape here that blends this step towards the end of the diffuser. You've got a hole here to access the starter motor. You know, when they start the engine, they need to go with a long shaft, go in the gearbox and start the engine. So you need a hole here. And actually, maybe we want to close this hole with a trap or do something better than having just a hole, and change the shape of the boat. And the last thing you will look at is all these fins, these veins in the diffuser. So you've got 6 of them. You can have more, but first of all, you can see that there is, if I look at the box again, regulation, you can see clearly that you've got 2 different heights. This is called Z0 here. This is called Z50, so 50 millimeter higher. And you can see that the veins going off the diffuser, they cannot be lower than certain height in different places. So you have to be careful when you design. And then you can vary their profile. So each vein can be looked at separately. So you can imagine the number of iteration you need. If you don't want to change all of them at once, so you want to maybe optimize this one, so you will give it a 5-degree angle in one direction or the other. Is it better or worse? And then you do the same with this one. And this is how you optimize a diffuser. You just play with the parameters and do small steps and see if it's better or worse. The last area is this area here near the tire. We can see that we've actually reduced the diffuser. We could have had the kick of the diffuser going all the way towards the tire, but we've decided that we want a flat section here without any diffusion effectively. And the size of this cut near the tire, all this shape is very sensitive. So if you change them, it will change the performance. So as you can see, there's a lot to do in just a small area like the diffuser. So you can imagine for the whole car how much time it will take to develop it properly.
Okay, Nick, we have 3 more questions we can answer, I think, in the time. First of them is by Darren. And Darren's question is, would following a car that has a large underbody tunnels and minimal or no wings have less or an effect on the second car, or is it similar?
It's hard to answer that question. First, we would have to test. If it's got no rear wing, you can imagine that yes, the wake will be smaller. But you know, I don't think it will happen anyway, because the cars are all pretty much similar in dimensions by regulation. So this, you know, you won't see this scenario happening anyway in Formula One. Okay.
Yes. Okay. Then the next question is by Luis, and his question is a little bit complex. And he asked, which method is, in your opinion, better to cool the brakes, the blown axle or the traditional method that is, for instance, the Mercedes team use? Because watching a simulation, the airspeed seems to be greater in the inner part of the tire rather than in the exterior part.
Can you just repeat the options he's talking about? So which exit options?
The method for brake cooling.
Yeah.
Is it blown axle or the traditional method?
So what is the traditional method? I think Yeah, I think the question is about where do we want to exit the air that cools the brakes, yeah?
Yes.
I understand it like this. So, okay. I'll do a slice here trying to show what we're talking about. So I'm going to slice through the front tire here, okay. We are missing obviously some components inside, but we can still understand what's happening. So first of all, the air cooling the brake ducts, inlet here to let this air come in. So that's easy. And then it comes in and it will go inside this big chamber towards the brake itself and the caliper. And at the moment, this chamber is completely closed and the only exit is on the outboard. So the air is going to go through the spokes of the wheel and exit completely on the outside of the wheel itself. This is the preferred solution because it is hot air that will exit, probably at 150, 200 degrees or more. So it's got low energy. So you don't want this air to be sucked in under your floor. So it's better to exit it on the outboard. So it will just stay on the outboard and not influence the car downstream. Having said that, it's not always possible to have a very good cooling efficiency if you only do this. Why? Because this is you are limited by how much air can go through the wheel itself, and you're going to start to be limited by the exit. So when you have brake problem temperature issue, you will start to have to create some holes in this chamber so the air can exit somewhere else. And if you create some holes on this face, inboard face, the air is going to exit on the inboard face, and that will lose some performance downstream, but you have to do it because you want to cool your brakes a bit better. So it's a compromise. If you can exit all the air outboard, it's better in theory. Most of the time it is, but you might have to cut some holes on the inboard, inside face, to cool your brakes better. You might see that on certain tracks, they have to open these holes. On other tracks, they won't, depending on how much brake energy is needed to be cooled. Hope this answers the question.
Great, Nick. Last question for today by Joel again. What is the purpose of a monkey seat in a F1 car? Joel wants to know what is the purpose of a monkey seat in a F1 car.
The monkey seat. We don't have a monkey seat on our car, but it doesn't matter. I don't really like it. No, sometimes you need it. So I'm going to show it on a picture. Will I find one here? Yes. Okay, actually that's a good illustration of the monkey seat. But more seriously, the monkey seat is this wing profile, double element here, at the center under the rear wing. First of all, it can only be this size and not more by regulation. If you look at the box you can design your car into, you can see that it's a bit hard to see, but you are not allowed to have this wing in this area. It can only be in the center, okay? Which is why it's not wider than this. What it does is create more downforce and more drag for your car. So it's the same as a rear wing, but it's a smaller version of it. Having it or not having it actually will depend on which track you are racing at. To go in more details, we look at the efficiency of this element. If you add the monkey seat, you will have more drag and downforce. You look at the ratio of this additional downforce and drag, and it's always pretty close to break even. So it's always pretty close to 1.5, for example. So you won't use it at Monza, but you will use it at Monaco to make sure it makes the car go faster and not slower. So that's the monkey seat. That's what we call the monkey seat. I think the reason is that you can sit your monkey on it.
Nick.
if you've got one.
Nick, thank you very much also for this answer. Yes, I think we are now at the end of this session. We will have the last session of this series next week, Friday, which will be also about overtaking, aerodynamic of overtaking. Yes, I have to say again, thank you to everyone, to all the guys who participated in our today's workshop. For sure, also to you, Nick. You gave us a great introduction again into this F1 aero stuff. And yes, hope to see you all again next week. And I wish you all a nice weekend. Bye.
Thank you. Bye-bye.